This is our first panel for this afternoon, and the chairman is Mike Thome, who's the vice president of programs for SAIC. And this panel will look at emerging technologies and how they can help with aviation, with the sustainment and the maintenance. And with that, I'll turn it over to Mike.
Thanks, sir. Appreciate it. Is this hot? Okay. Yeah. So I got this. We were down here for the industry day a couple months ago, and shortly after that, I got home and I get this letter in the mail with General Sinclair's signature saying, "Hey, I understand you come back for Luther Jones, where you be the panel for emerging technologies." I had to read that again. At first, I thought he wanted me to be on the panel, but when I saw the part about chair, I said, "Okay, I think I can handle that." So I tell you what, I want to go through real quickly some key points about each of the individuals that are sitting to my left. It's amazing the expertise we have here. I think this panel flows nicely with Mr. Jensen's discussion earlier, and then followed by Colonel Morgan and the 160 guys. So to my left is Don Duran, who's project lead for Camber Corporation, supports the Aviation Engineering Directorate, part of the AMRDEC. He's responsible for the corrosion and toxic metal reduction programs, airframe condition evaluation, and the corrosion prevention and control evaluation programs for Army aircraft. He's a retired U.S. Marine Master Gunnery Sergeant in 22 years. He's managed departments at all maintenance levels, responsible for airframe structures and component overhaul and repair. He is he's involved with the flight, test, and envelope expansion of the tilt rotor test vehicles at Pax River, and his work has included evaluation of advanced composite structures on the rotorcraft. He's a graduate of the University of Maryland and the University of Texas at San Antonio. To Don's left is Scott Gray, who's the president of Elevate Systems. Scott, after 25 years in the defense industry, he and his wife, Marcella, started the company in 2012. They specialize in obsolescence and sustaining engineering support. They utilize state-of-the-art 3D modeling, and if you've been to their booth, they've got a neat demonstration set up out there on 3D printing. So if you haven't been there, I highly suggest you find time to go by later today. In less than 3 years, the Elevate has become known across the service as a leader in additive manufacturing and modeling areas. He is a graduate MBA in operations from St. Mary University and a BBA in management from Angelo State University. And to Scott's left is Earl Thomas. Earl's a native of Pennsylvania. He's recently retired in February of 2011 from the United States Marine Corps. Oh, I'm sorry, United States Army. Oops. Oh, that's right. One was a...
There's only one allowed.
Yeah, that's right. He served in numerous aviation locations in Germany, Fort Riley, Camp Humphreys, Fort Eustis, and Fort Drum. He's graduated from the first sergeant course, advanced maintenance, ANOC, BNOC, PLDC, the advanced composite rotor course, advanced composite fabrication course, and he earned an associate's degree from Barton Community College and a bachelor's from Southern Illinois. And then to Earl's left is Kevin Rees. I think a lot of you probably know Kevin. He's the chief of the Maintenance Engineering Division for AMRDEC here at CCAD, responsible for coordinating all maintenance and sustainment engineering support for the Army helicopter operations worldwide. His education, he's got a master's in mechanical engineering from Georgia Tech, an MBA from Texas A&M Corpus Christi, and a Bachelor of Science in Mechanical Engineering from Rose-Hulman Institute of Technology. And I'd just like to point out that some of the awards, and one of the things when I met Kevin 2 months ago when I was down here that I really appreciated is I have some folks down here supporting him on the value engineering side, and he'd recently been up to to Washington, D.C. to receive some outstanding achievement in value engineering. And one of the things that really stuck out that I appreciate most was the fact that he said it wasn't about me. It's about the folks. It's about the folks in that office. And that's what I've seen in all the presentations here today. It takes a team. It's the whole, it's everybody pitching in to do the right thing for our warfighters, and so many of us that have been there and done that, and now we're on the other side trying to contribute to that. So I really appreciate the opportunity, General Sinclair, to be here on a member of this panel, and with that, I'll turn it over to Don.
Thank you. All right, first of all, there's nothing sexy about my topic. But I will say that our 160th brethren came up here, talked a little bit about corrosion and the importance of corrosion and what we're dealing with. The only thing that I can tell you that I hope you take away from this is we really do spend millions upon millions in wasted parts that we could absolutely use in better places other than trying to deal with these corrosion issues that we're dealing with. First topic I'll be talking about is the identification of corrosion, some of the resources that we use, and then some of the new technologies we're involved with. This first depiction is a H60, and all this is our 2014 corrosion-specific data for the airframe condition evaluation. We also conduct a corrosion prevention and control evaluation. Now, the significance of this depiction is how little corrosion is reported on these specific indicators. This is a huge success story for the 860. We take this data and we trend it. We conduct analysis. And again, this is only the corrosion portion, not everything else that we document, strictly corrosion. You can see that from 2010 to 2014, you start to see a decline. Well, years prior to that, these depictions were absolutely terrible. We had a tremendous corrosion issue. We worked hard with our partnership, with our OEMs and so forth to reduce this by means of corrosion prevention advisory teams and, of course, conducting the analysis that we work. And again, these are all requirements out of the AR 750-1 sustainment. What do we do with this data? So we identify these hotspots. We take these to, again, our manufacturers, and we show them where our problems are at. Now, these are the evaluation points that our evaluators find as they're out there conducting their inspections. They'll go through and find each one of these points. We take them, we try to develop a repair for them, and which we're trying to do as we speak. We work with Sikorsky, we work with the PM office and so forth, and try to address these problems. Now, resources. Years back in a very similar forum, General Pillsbury fielded a question from one of his unit commanders, and that was, are our aircraft safe? Are our warfighters safe? Our aircraft get this gray-looking appearance to them. What is wrong with them? Are we a target? Are we lighting up in the dark? Well, the question had to be answered. At the time, the AMCOM Corrosion Prevention Office was tasked to do that. AEM followed up with them to rewrite the 345 manual, which is the Army Aircraft Paint and Markings Manual. We discovered that not only was the coloration an issue, but thickness was probably the biggest issue we were dealing with. Our coatings were so thick, they were creating a mudding effect that was embedding corrosion inside the paint itself. So where we thought more was better, the aircraft was actually corroding. Every time it'd come back here to CCAD, these guys would take it down to the skin, and we'd see how bad the damages were. We found that they were pretty extreme at the time. We also realized that weight varied quite considerably. We could weigh 100 pounds more in the back end of the aircraft, and this is in the case of the 60, than we did in the front end. And these are on a brand new 60M aircraft. Of course, that meant fuel, CG issues, everything else that we're trying to avoid and correct. So these are things that we've worked on. The 344 manual is a Navy-funded manual. The problem with this one is that the Army's inputs weren't making it into the manual. We've got our own appendix, but we weren't actually getting our inputs in there, so our maintainers, our users, were not getting the information they needed specific to their aircraft. The MIL DTL 5372, the only reason I'll mention that is that would have answered all the questions from the two technical manuals above, but it was never referenced in any of our manuals. So we had a big disconnect, and we knew we were going to have to go in there and rework all of this. We've been a part of this now for at least 7 years. I think we're making some great progress. I'll talk more about the last two on this slide. So the typical 60 or any one of our aircraft looks like that top right depiction. Okay, you've got a little bit of everything. That grain effect that you see on the door is what our commanders were complaining about. That's called marring or chalking. And what it is the flattening agent that was being used by ARL at the time was a silicone-based or silica-based product. And as you scraped it and sanded it on, just like you do with sand, you start to get that white effect. If you look right above it on the engine nacelle, that's the new technology paint. That's the polymeric bead paint. And that big change came, again, out of this study that we did, years and years of data collection, made the improvement. Everything you'll see from here on out with the new technologies will look like that engine nacelle and not what you see below that. The TAG-9 Environmental Security Technology Certification Program, ESTCP, is being conducted here at CCAT. We're working closely with this team, with them to get the program off the ground and start coding existing gearboxes. Those are already fielded instead of those that are being brought into new production aircraft like the 64 and soon the H-60 aircraft. Low solar loading CARC. This is a new CARC paint. And the issue with this one here, or the great thing about this one here, is its ability to reduce heat on the aircraft, specifically on the rotor blades. The more our aircraft become composite, the more and more important this is going to become. Our resins, my experts here will reinforce this, our resins start to break down at about 180 degrees, 160 to 180 degrees. Well, any flight line on a hot summer Texas day with all that iron oxide mixed into that coating is going to start breaking down your resins. So this new coating significantly, and I can tell you that at a minimum, 40-degree difference is what we're starting to see now, just in reflectivity or the reflectance reduction in the solar absorbing characteristics of this. So this is a great improvement, something that we've already started testing. I was just out at a demo a couple of weeks ago, and we plan to have that here at CCAT soon enough to do demonstrations here. This also is in the 53072 spec that I mentioned before. This specific one will mean no change to the manuals. Means no change other than an application change. You will see a little coloration difference, and there they are. The one on the left side are all these low solar absorbing or low solar loading CARCs. It's about a 2-shade difference that is well within the spec, and that's all you should be seeing. But again, the functionality of it's just fantastic. Class N primers. We're working hard with ARL, the AMCOM G4, again, to reduce toxic metals, to make it safer for all our employees, all our artisans and maintainers out there. One of the best things that's come along is metal-rich primers. And the one that we're having the most success with right now is aluminum-rich. Aluminum-rich is showing some tremendous promise. It is at or better than the MIL 23377, which is what we use on the aircraft now. And again, based on testing that we did last week and more to come. The mag-rich is also showing promise. We're looking forward to see if that's going to improve in any way, shape, or form, but we think it'll advance along with the aluminum-rich. Here's a couple of coupons that you can see. The one on your left is the aluminum-rich primer. The one on your right is your existing primers, okay? That's how much better it's doing. This is with some of the hardest, again, 775 aluminum with composites on it and our hardware testing. And all mixed metals, all mixed applications, and we're seeing the results that you're seeing there at 3,000 hours of salt fog. Conversion coatings, toxic metal reduction project. This is something that we're deeply invested in. Right now where we're at is we've got a demo that's going to be occurring. We're looking at about January the 11th to bring the team down and do a spray-on application of an iodine replacement, of the TCP replacement. What this means is, again, safer conditions for our maintainers, our artisans and so forth, providing them safer environment and reducing chrome out of these products entirely. Again, this is something we've got a sunset date here in a few years that we have to make a big impact on reduction, if not elimination, of chrome use. The list of selections that you see there, those are the different products that are being tested now. We'll down select, get those to about 3, and that's all we'll bring here. This is going to be a drop-in replacement for our CCATers. Ought to make life very easy for them. Okay, these are what we're going to use in order to conduct our testing. We'll be using these BER nacelles here. I've got a couple of these already set aside. We'll be taking these, spraying different sections of them. We're also going to take a few of the panels that are on these nacelles now. We're going to do the same application, and we're going to send them to Cape Canaveral to make a comparison between their conditions there and our conditions here. We've got a feeling our conditions may be a little bit more aggressive than Cape Canaveral's because, again, they don't deal with the refineries and manufacturers that we have all around here, our friends to the south, and, of course, salt spray all about. Again, one of the latest things that we've done and really great is that our non-skid material may seem very insignificant to you, but when you see how much damage the existing non-skid we use on our aircraft today are causing to these structures, you'd be amazed. The stuff that's listed there was intended for ships, for steel application, for loading of trucks and tanks and so forth, not for aircraft aluminum surfaces. So as our guys are out there working on these surfaces, they're just rubbing this gravel into the skin, into the aluminum, causing damage and working it through there. So, you know, we found that we can take the same polymeric beads that improve the color of our CARCs, and we've enlarged them, added them to the CARC, and they make a great abrasion. So we're adding this, and we'll be doing a demo here as well. A couple of pictures of what it looks like. Again, it doesn't look like a gravel bed. Are there any questions?
Questions? Somebody.
I'm okay.
General Yellen's got a question.
I'm okay.
Yeah. General Riggs has got a question.
I don't have a question, but I just want to say thanks on behalf of the entire CCAT workforce and anyone else that's doing this painting for the Army and other services. You know, eliminating Chrome 6 from our environment is a big deal. We can't do it fast enough, and I appreciate you guys stepping out on this. As I understand it, we're going to be well ahead of any deadlines set by OSHA or anyone else, but the main issue is to get those hard metals out of our plants. So thank you very much for that.
That's deeply appreciated.
Tim Sassman.
Tim Sassmer at Boeing. I'm kind of curious, in working with the Navy and some of their aircraft, B-22, working out of Cherry Point. Similar conditions in some ways, close to the salt, not quite as close as we are here, right? I'm wondering if you've had a chance to talk to what they're doing on corrosion. They have similar issues and shared that what you've been able to accomplish with them, because I know they're going through even, as hard as it may be to believe, even more corrosion issues than we are based on their constant salt environment they're working on with their vertical lift aircraft.
No, absolutely. I will say that we are working closely with NavAir, Craig Madsdorf and his group to solution a lot of the issues that that they've dealt with, we're dealing with. They actually partnered on the non-skid, and the aluminum rich is one of their projects. So we're kind of working off of them to work that particular project. Some of the things that we're learning, again, we're looking at a lot of more shipboard operations for Army aircraft. We're trying to take as many of their lessons learned and apply them to our aircraft themselves. But yes, there's a tremendous amount of information exchange at every one of our corrosion prevention advisory team meetings. So we invite them, we invite the Air Force as well. We work closely with the sister branches.
Okay. Thanks, Don. Scott?
Thank you. All right, while they're bringing that up, good afternoon, everybody. My name is Scott Gray. I'm the president of a company called Elevate Systems, and we're based in San Antonio, Texas. We're a relatively new company. We've been in the defense industry for quite a while and decided to branch off on our own and support our clients in a manner in which we think they need to be supported and try to eliminate, I'm sorry, OEMs, eliminate proprietary data one part at a time. So, and by the way, our chief engineer graduated from the University of Texas at San Antonio. We thought you might like that. That's right, go Roadrunner, do it, right? Roadrunners. All right, so I just wanted to preface this also. This is a presentation I recently gave to the Air Force Small Business Industry Day out in Macon, Georgia. And the timing's perfect for this because you're hearing a lot of activity about 3D printing and additive manufacturing and a lot of questions about certification and putting parts on weapon systems and things like that. So this is one of the key things that helped us start our company here just a couple of years ago. And again, let me just start off with an actual solution. 3D printing is a very disruptive technology in a very good way, but it has to be used the right way. We are today, Elevate Systems is flying on 4 B-52 Stratofortresses, a 3D printed part. And this is a success story, so I can tell you, and I know the folks here are doing this right now, or at least moving in this direction, thinking about how does additive apply to a depot like this. Not only how does it apply, but how do you do it? How do you have the engineering staff that understands 2D to 3D? And even if you understand 3D, do you understand 3D printing, 3D design and 3D modeling that will culminate in a 3D printed part? And then the last piece of that is, once you've done that, how do you get the authority to put it onto a weapon system? So this is a great example. It's a great poster child for the Air Force in this case, out of Tinker Air Force Base, in a lesson on how to do it. And in our case, we were very fortunate to have a contract shortly after we formed our company based on, it started on a Congressional Plus back in the good days when we used to have some money, we could do some things for some of the weapon systems. But on the Tinker asset, they have a, it's a radar blower motor system. So you were talking about non-sexy. This is not very sexy, but it's very, very necessary for the aircraft to be able to have cold air blown on the old avionics on the radar system for engine startup, taxi, and takeoff. So this was designed approximately 1957, 58 time frame. And I have a couple of assets here, but this is the original impeller. You're welcome to come by our booth and take a look at this. Very well designed. It was very over-designed with aluminum, with sheet metal. It was hand-riveted, hand-crimped, and it's been in service for over 50 years. Well, this is not the main problem on the blower system. It really is the electric motor. You'll see down there your third picture from the left side. And that's a Hamilton Sunstrand 400 hertz motor. And then, of course, we have a housing, an impeller, and some other parts and pieces. It's not rocket science what we did. We basically do, we call it slice and dice and shake and bake. Reverse engineer, take the assets, determine, do a little bit of a quick study up front. How do you determine, we were just talking a minute ago, how do you determine the viability of a part for 3D printing? It's so relatively new, not really the technology, but the use of it. What are the factors that we're using today in order to identify a part and say, yep, that's a good part? Well, again, this is a great poster child because this is a non-CSI item. It does move. It is spinning 11,500 RPM in the aircraft, but it's not structural. If it were to break or fail, there would be no negligible effect to the aircraft, but it is required, again, for engine startup, taxi, and takeoff. So we have a new electric motor. As an engineer, we're not a manufacturer, we're an engineering services company, so what we typically do is create tech data packages, right? That's the key to life. And now we call them advanced technical data packages. And why did we add that A on the front of it? Well, because we have this new stuff called 3D models. So when we create, we use SolidWorks as a platform. Many of our clients and many folks in the industry that are not doing airframe and structure are using SolidWorks as their tool, so that's what we've adopted and been using for several years. The impeller, again, about 75 parts, hand crimped and hand riveted. And then we did have to reverse engineer. You see a back plate and a filler strip, and people think, oh, it's no big deal to reverse engineer that. It is a big deal to reverse engineer it properly and then to validate what you're doing. And then create a TDP, a tech data package that is sufficient for competitive reprocurement. Because that's typically the case, is the clients want to have data. How many times have we all seen in Fed Biz Ops, no data available? Over and over and over. So in this case, we did a dimensional inspection, redesigned and modeled the impeller, and then we researched any off-the-shelf parts, which there are some in this case, and then create the preliminary drawings, and then we actually go out to manufacturers just like you guys would do. We follow the Federal Acquisition Regulations. We'll do a source of sought synopsis in Fed Biz Ops to try and find folks that want to come in and compete for this, because one of our taglines at Elevate is we are manufacturer agnostic. Right? It doesn't matter to us who the manufacturer is. We care if they can build to print. And if they can build to print, if they can deliver it in the quality that we expect, if it's ISO 9000 or AS 9100 or whatever it is, as long as it functionally operates. And any vendor that we use has to do one of two things. They have to follow our print with no engineering deviation whatsoever, or if they have to do engineering, as the electric motor company did here, they have to give us 100% of their technical data, or we will not do business with them. Plain and simple. So you can see our first, on the upper left there is the original impeller. The second one is the 3D model that came out of SolidWorks. The third one was printed, where? At the University of Texas at San Antonio in the College of Engineering, because we didn't have a 3D printer at the time. And so Dr. Amali Agrawal was the dean out there, and he was nice enough to print this for us. And then our customer, we coordinated the whole thing with our cognizant engineer out at Tinker, a guy named Chris Duffelmeyer, great engineer. And he said, let's go into metals. And so we did a 3D printed in stainless steel. So the one you see down there on the bottom left, that's a stainless steel version of this impeller. It was printed for us because we have prototyping printers, and you're welcome to come by our booth and look at, we have a what they call a prosumer, which is called a Cube Pro 3D Systems printer that we use in our office. But these are not the high-end printers that you use for production. But this was printed for us out at Rock Island Arsenal, as a matter of fact. They have a GoCo at Rock Island. I think it's called Quad Cities is the name of the 3D printing company that's sitting there on post. And we were able to contract with them to do the metal for us. And then once we did stainless steel, you would never put that on the weapon system, way too heavy, but we did it just to do a prototype. We moved to aluminum, and that was the goal, because I have the aluminum printed one here, and obviously the aluminum original asset that we started with, and they're almost exactly the same, except this one has one piece as opposed to 70 some odd pieces. Once we finished that, then our customer said, let's go one more step and let's look at a thermoplastic and see if it will meet the intent of what we need and see if it can do the same job that the aluminum impeller would do. So we ended up doing that, and we're using a thermoplastic called Ultem. Many of you are familiar with Ultem. The great thing about Ultem is it's chemical and heat resistant. And remember, this spins at 11,500 RPM. So we had it printed. As a matter of fact, now, 2 years ago, it wasn't as prevalent, but now you can get this almost anywhere. But what do you need? You need a 3D model. You need a good 3D model to do what you're doing. We can now send an STL file, which is a 3D representation of the part. We don't send drawings anymore. We send an STL file to the printer. And since we're in San Antonio, we have a printer we use that's in Austin, Texas. And we have this in our hand the next morning. It's simply amazing. Once you have a validated 3D model, you just have to have someone that has a printer. I understand here at CCAD you have a Stratasys printer. That's what this was printed on. I applaud you for that. I applaud CCAD for moving in that direction. Every engineer needs to have one of these mid-level 3D printers sitting in their offices, because I'm telling you, your productivity is going to increase.
Y'all can share the one you got, I'm watching my costs.
You got to watch out. Your colonels will start asking you for a case for their iPhone 6 that you'll have to print out. Again, we did the fused deposition modeling, which was the thermoplastic version, and then we did the laser sintering, two totally different processes. If you haven't seen selective laser sintering, it's really pretty cool. They basically take a 30-micron layer of metal powder, if it's aluminum or stainless steel or titanium, lay it down on an elevator bed, hit it with a laser based on your 3D model, and then that's why they call it additive manufacturing, because it does it layer by layer by layer. The aluminum impeller took about, I think, 6.5, 7 hours, 8 hours to print. There is some post-processing. A lot of people think you hit the print button and take it out and you put it on the aircraft or the weapon system. Not quite that simple yet, but there is some post-processing that has to occur. And think about the cool part of this, the capability that it's parts on demand, basically. And a lot of us are thinking about that. We've done a lot of work in the C5 Directorate out at Warner Robins over the years and C141. And they had an idea about 2 or 3 years ago to have non-critical, non-structural parts on demand sitting at their forward operating locations. Pretty progressive thinking that. You know, if you get off, land somewhere at Dover Air Force Base, you're missing a part, hopefully you have a database, and you hit the print button, go have dinner, come back, and there's your part. You put it on the weapon system, then move on out the door. Think about your procurement costs. Now, you can't ever forget the 3 letters NRE. Non-recurring engineering. If you, again, I can't emphasize enough, if you don't have a valid 3D model, you're going to print junk. So that's why you have to learn. There's 3D to do manufacturing, CNC, and there's 3D to do printing. So I recommend in our government, our organic organizations that are trying to do this, just like you're doing here, you have to provide training to the engineers. They have to understand the nuances and the differences between 3D modeling and 3D modeling for printing. Very fast turnaround time. I tell a story that when our Tinker engineer came to San Antonio for our very first sell-off of this asset, we tested it and we had an issue that we were not aware of because we're only handed the old asset, right? We have no data, we have really no failure data, we just have the actual mechanical asset. And we had an issue on the impeller because we simulated exactly what was in the aircraft. And it turned out we had an overamping issue because of the small envelope space this thing has to spin up in very quickly. So as we do in San Antonio, the home of the University of Texas at San Antonio, we basically told our engineer from Tinker, why don't you go down to the Riverwalk, have dinner. Everyone loves to go to the Riverwalk, so he did. We had Alex, our engineer, change the design. Took him probably about 5 minutes, 10 minutes in SolidWorks. We emailed the STL file to Austin. We had it in our hands by 8 a.m. the next morning before the engineer walked in the door. That's impressive. That is fast and it's impressive. Very quick turnaround. Okay, I've already talked about the fact that we did 1 aluminum, 1 thermoplastic resin. Now, the primary differences between the two, you can imagine the aluminum, very strong. Well, the Ultem thermoplastic is almost as strong. It performed almost exactly the same. And guess what? To print the aluminum from a validated file is about $3,200. It's really not that expensive when you think about it. But the Ultem thermoplastic resin is $300. You're talking a 10x savings. So that drove some decisions on the part of the cognizant engineer that owned the aircraft, because a lot of people, the number one question we get, well, first question I always get, can you print a gun? Yeah, we can print a gun. We're not going to. The second question we get is, how did you validate this and get the authority to put it on an aircraft? And that's what we did with the cognizant engineer that owns the B-52. We did testing to it. We did not do endurance testing. The reason we did not do endurance testing is because, again, it's non-safety, it's non-CSI, and it's non-structural, and it's $300. How much do you want to spend on endurance testing on a $300 item? Guess what? If it breaks, the plane's still going to fly. It's still going to take off. It's still going to land. So you have the ability to R&R, right? Remove and replace. And guess what? You can print on demand. Now, that's a pretty cool deal, right? Pretty cool deal with the technology, right? So here's what we did test. We tested volumetric airflow, RPM, vibration, torque, and amperage. And again, we said we did an endurance test because it just wasn't necessary. And that was not our call. That was the engineer's call that was in the Air Force. And I think it's the right call in this case. Here's where I told you about we had that problem, that overnight problem for the overamperage situation. Well, what they do, we did two different ones. We removed every other one, then we removed every third one, and we ended up using the, I think it's the second one. That's the one that I have here. And again, you're welcome to come see it. So now, and I talk a lot about the impeller, we took the housing, and guess what? We reused it. There's no purpose, no sense in having to totally reverse engineer a housing that's perfectly good. All we did was we stripped them, we took out any dents or dings or problems they had, and then we repainted them, and then everything else is new that you see. Again, the back plate, the filler strip, and then the electric motor. And there's the end asset that we have today, and I like to emphasize again, we're not a manufacturer. But the Air Force asked us to sign off on the drawings, which we did. We don't typically do that. We typically give the data to our clients, and they own it. So they asked us to put our cage code on this. So now, unbelievably, we are an OEM. But we're a very different OEM than what you're accustomed to. Because not only did we deliver 5 zero-time assets to Tinker Air Force Base, we delivered 100% of the technical data, the native CAD, the 3D models, the tech order information, because we changed materials. So guess what? Now the Air Force, in perpetuity, can buy these assets anywhere they want to go buy these. They can come back to us, which they just did, because they have a MICAP on the aircraft, and it makes sense. But their savings, their cost reduction, and time from start to finish has been so drastically reduced that this is proving that this is the way to go. We just received an emergency buy, as a matter of fact, because again, it's MICAP situation. They have 10. We just delivered 9 out of 10. Why? We've already done the engineering, right? We already have the validation of the data package. So let me close. Not everything can be 3D printed. It's just not possible. But you know what? We can 3D print things that you can't manufacture. You got to think about that too. Again, the current focus is on non-critical and non-structural. 3D modeling is available everywhere, but again, we talk about there are issues, there are differences between modeling for printing as opposed to modeling for manufacturing, and you got to train your folks. Other issues on certain, what testing is acceptable, what's the function of the part, and what are the cost trade-offs. These are all things that the information is not difficult to come up with. So I think that's it. I don't need to talk about these other things. I will tell you this one right here, we did 2.5 years ago. That is a 3D printed, it's called a cold air diffuser. The rest of us call it an air conditioning vent. But it's a cold air diffuser that's on the C5. We did the traditional metal manufacturing you can see there, and then we did 3D printing. And it was very successful. That's all I have. Thank you. If you're welcome, come by the booth and see our printers.
Any quick questions? Oh, we got one back here. Stand by.
Sir, Lieutenant Colonel Kedemeyer, PEO Aviation. A question for the room, but you've got it on your slide. Maybe you know the answer, maybe not. How do you get airworthiness on an added manufacturer part?
It's a great question. We get asked that all the time. And the engineer that we dealt with at Tinker Air Force Base is the cognizant engineer for this piece of equipment that goes on the aircraft. We had testing requirements that we had to follow, and And we have them all in our notebook. You're welcome to come by and take a glance at it. And then Chris Duffelmeyer, had to go brief the B-52 Configuration Control Board, the CCB, to get authorization to put this on in a test environment. So January 15th of this year, they got the approval to install 4 of these on the airplane, and we've had 0 incidents since. So I don't know if that answers your question. The authority came from the Configuration Control Board engineering staff of the B-52 airplane.
Hello? On the airworthiness qualifications, it's not really that different than a non-additive manufactured part. It's driven by the particular part and its application, you know, the loads and that kind of thing. So we've qualified additive manufacturing for some repair processes using cold spray, and you have to look at that particular part and where is the repair, you know, how's it being loaded, and just run the same process as you would with a new machined part or plated part or anything else.
Okay, good question, thanks. Thanks, Scott. Earl?
Oh, I'm sorry.
Good afternoon. I'm Earl Thomas. I work for Southern Research out of Birmingham, Alabama, but I actually work inside the prototype integration facility on Redstone Arsenal. And I'm going to talk a little bit today about composite repairs and some of the things that we've been doing. I've picked 3 of the efforts that are just now coming to fruition that we've been working on that we'll start seeing in the field. Each of these I'm going to go over in detail, but I'm going to talk about the UH-60 Alpha Lima Mike engine cowling, the UH-60 Mike main rotor blade, and then the Gray Eagle. The UH-60 engine cowling. The current engine cowling design hasn't changed since the Black Hawk was introduced. A lot of the engine cowlings we have out there right now have been in service pushing 30 years. It also functions as a work platform. Anyone who's ever crawled up around on a Black Hawk, you've folded that open and stood on it. Well, there's been a couple instances where those engine cowlings have now failed. There have been a couple of people who've been injured when they fail. Unlike metallic structures kind of give you an indication when they're going to fail. You see the blushing of the metal, you see the stress cracks form. Composites don't really do that. Composites are good until they fail. They don't tend to tell you they're going to fail. One of the things we found, the program manager asked the prototype integration facility to look into this and try to come up with a fix. Upon investigating this, one of the things we found was the way that the current panel was designed, where the hinge mounts, there, that's 8 plies of fiberglass that are wrapped around that hinge, which is great for mounting to it. But right past the hinge, it steps down to 4 plies of fiberglass. Fiberglass is very strong, but over the years, with it getting damaged in that area, and it was interesting, I got asked the question, how did I think it was getting damaged in that area? And I took out a tape measure and kind of measured where those damages were. And for those of you who remember the old Army red toolboxes, the exact dimensions of pushing one up on there. So it was one of those things that over time, toolboxes being pushed up on there, it started damaging, along with being kicked by shoes, having debris on your boots. So the challenge was how to fix this. Not particularly the ones that have already failed, but how to address the ones that are currently out there in the field. And there are currently 2 ASAMs out there on the engine cowling. Cannot be used as a maintenance platform in its current condition right now. What we did is we developed a doubler that would go over top of that hat section on the edges of the engine cowling where that critical area is. The doublers are made out of 4 plies of T300 carbon fiber with the plies orientated in the direction of the load, of the stress. At the top of that hat section, it's 4 plies on each side, and at the top of that hat section, they overlap. So you end up with 8 plies of T300 carbon fiber, so it becomes extremely, extremely robust. We then put a couple of plies of fiberglass on top of that to protect the carbon fiber. So we now have an indication. If you see fiberglass being broken through, no problem, just do a normal fiberglass repair over it. As long as you're not damaging the carbon, it's fine. This is a CAD drawing of how it's installed, there's two types of decks out there. On the engine cowlings, there's a recessed deck and a flat deck. We've designed doublers for both of them. We've tested these. A brand new engine cowling from the factory will fail at about 2,100 pounds. We took a brand new engine cowling. We induced damage in two spots on there, right at that critical area just past the hinge. Made a 1/4 inch wide, 1/2 inch deep cut. Then we put our doublers on there. We're breaking cowlings at about 2,700 pounds. However, it's not our doubler that's failing, it's the aluminum fitting. The aluminum fitting will only go to about 2,700 pounds. So the big question mark is how much load can our doubler take? AED actually had us make test coupons so they could pull them to failure. And it's to the point where somewhere around 3,000 pounds can be put on there if you didn't have to worry about the aluminum part. Our structural handle, about 3,000 pounds. This effort is moving into verification next month, and will start being fielded. This thing worked for everybody else, but it's not working for me. It'll start moving into production and fielding sometime probably within the next 6 to 8 months. So this will be coming out very soon. Part of our effort is to actually publish the procedures. It will not be coming out as an MWO. To do it as an MWO would take more time. It'll come out as just a repair kit that will be addressing that ASAM, and it'll actually go into the technical manual. So the tech data package and everything belongs to the Army. We're going to publish it right into the technical manual. So that'll address all the current issues on the engine cowling and get back to using it as a maintenance platform. Being an old maintainer, I can't imagine how difficult it is right now to try and work off of a B1 stand instead of being able to get on that engine cowling. The Mike model main rotor blade, the wide chord main rotor blade. This was one of those programs where the Army didn't buy the tech data package for the main rotor blade. Sikorsky maintained the tech data package. The program manager came to the prototype integration facility and asked us to develop some repairs to address some of the common damages on the main rotor blade. Luckily for us, the Mike model main rotor blade, while it is different than the Lima model main rotor blade, its basic structure for its pocketed honeycomb core area and skin is identical to a Lima model, by and large. Materials-wise, it's basically identical. So we were asked to address 3 areas. The first one was dealing with voids. Voids and punctures in blades are very common, especially punctures when you're flying in airspace that also occupies bullets. The Mike model blade as fielded, you couldn't fix a hole larger than a 1/4 of an inch puncture. You could do a repair for a 1-inch hole, but it was almost impossible to execute. It just didn't, the procedure as written wasn't going to be easy to do. What we did is the Army already has a huge supply of the Alpha Lima model plug patches. What we did is we took that plug patch and had it substantiated for the Mike model blade. So it will now work in the Mike model blade, and procedures are being written. We developed it, put it into an MEO that is now being worked down here at CCAD in your pilot Mike model blade program. So without increasing the logistics footprint very much, we were able to address a huge issue. The second area was the inboard trailing edge. The trailing edge of the Mike model blade is considerably wider in its chord area than it was on the Lima model. It's made of a unidirectional fiberglass that runs the span distance of the blade, which is great for the load in the span-wise direction. The problem is that inboard trailing edge is, everyone has ever been on top of a Black Hawk knows that that gets grabbed as either a handhold, it's also been a seat, and a lot of times when people are pre-flighting the aircraft, they'll push up and pull down on the blade, or on the ground when you're ground handling the blade. The problem is there wasn't a whole lot of strength in the chord-wise direction, so you would find cracks right in there running in the span-wise direction. So to address that, I sat down and I developed a procedure to patch it using existing materials that are already out there in the field that we already use, 7781 fiberglass cloth, 9396 resin, and developed a repair procedure that fixed that issue. We've done this a couple hundred times now. It's part of a current MEO that is being worked down here. Very successful program. The other one, and this one was a huge concern to pilots, where the anhedral tip is attached to the Mike model main rotor blade. It's bolted on and bonded on. Where that bond line is, there's a seam that's filled with an adhesive filler. The adhesive filler that was used at the factory, which I believe is EA 9395, has about a 2% elongation to failure. If you go up and you fly this aircraft for several hours, eventually, out there at that extreme tip, that adhesive starts to fracture. Now, it's only a filler, but when you see a straight line crack in a main rotor blade and you're a pilot, you're probably not going to want to climb on that aircraft and fly it. So we did a considerable amount of research to figure out exactly what it was. Was it failing only on the surface? Was it failing only in that gap? Or was it getting up underneath and causing problems in the bond line? We were lucky enough to find out that it wasn't causing any severe damage and it wasn't damaging the blade at all. It just needed to be refilled. The concern was if we left that crack in place, one, people are going to write it up as a damaged blade. The other one is that eventually moisture will work into that crack and will get inside the blade, which is another bad thing. So we developed a procedure using EA 9309.3, which is the most common paste adhesive the Army uses, and by placing it under vacuum and then heating it up and dropping the viscosity of the adhesive, we're able to flow it down into that crack and fill that crack using EA 9309.3, which has a 10% elongation to failure. So we shouldn't see it crack again, and knock on wood, we've been doing this repair about 3 years and haven't seen one come back yet. Again, that's part of the MEO that CCAT is now working under. One thing I wanted to bring up real quick is the new universal blade clamp for removing and installing blades. We found an issue when we started looking at Mike model main rotor blades. One of the things I was in charge of doing was keeping statistics on the damages and where they were located. Of the blades we were getting in that had voids in them, after a while I come to realize that over 50%, actually closer to 60% of the blades that had voids, the void was in the same spot, give or take 1 inch, right at the CG lines. So I was asked to look into it and try and figure out how that was happening. The easy thing was, well, I think it's the blade clamp, but I didn't have one, so I got a hold of a blade clamp, and the blade clamp, the new blade clamp goes on from the trailing edge of the blade and clamps up on the front edge. But there's also a clamp at the back end to push the foam up and contact it and hold it in place. The problem is when you go to remove the blade clamp, you don't have to loosen the clamp at the back end, at the trailing edge of the blade. You can just release the clamps at the front end and pull it off. By leaving that clamp down in the rear, when this gets pushed on from the back, especially if it's two soldiers standing up on top of the B1 stand pushing it on, they're going to push it all the way on until it hits the foam at the back. Because it's got foam, it's probably where it's got to go. Where we run into a problem, though, is now it overworks. When it's clamped up, you see in that little circle there's a hard plastic piece on this blade clamp. If that rear clamp stays in place and it's just pushed onto the blade, that hard plastic piece crushes into the honeycomb. On this blade we had here, we actually already had the damage on there, So we clamped it down. After playing with this for a little while, we clamped it down and realized you could take it off and that clamp still be in place. When we pushed it on forward, you could hear it crush the honeycomb into the core. When we removed the paint, you could visibly see that the area was voided out. So I put that out there just as a caution. If anyone's dealing or has any dealings with these blade clamps or soldiers dealing with these blade clamps, make sure they follow the printed instructions that come with it. The Gray Eagle, interesting airframe, all composite. The problem that came up and the way we got involved with it was the only way it could be repaired, because the Army didn't get any technical data on it, didn't get a repair manual. So if an asset was down in theater, the OEM had to send someone to theater to fix it. It would take somewhere in the area of 90 to 120 days to get an asset fixed when it was in theater. Obviously, can't imagine how the task force commander felt about it, but I know the program manager at the time was not real fond of that process. So he came to us at the PIF and asked us if we could develop repair procedures independent of the OEM. We said that wouldn't be a problem. All we needed was needed an asset that we could destructively, take apart and figure out how it's made. Luckily or unluckily, they had about 3 crash damage ones they gave us. So we went through a process with one of our partners on taking it apart and backwards engineering it. We took each of the components that we were on contract to figure out repairs for. We took them completely apart, burned out the resin, figured out the materials they were made out of, the resin systems that were used, and we also designed a zone maps so we could figure out exactly what materials were in each zone so that when it came time to repair it, you could have a table to go to and tell you how to repair it. So this is an example of the zone map on the engine cowling. And the other part that goes with it is this chart, which tells us not only where it's at, the zone that it's at, it tells us what the material is that it's made out of, and then how many plies are in there. We're then able to take that data and come up with a repair patch that will fix it. Keeping with that, we have a very common theme at the Advanced Composites Lab, is that we don't want to increase logistics at all. If we can do it with existing materials, that's the way we're going to do it. We won't repair anything made of carbon fiber with anything other than IM7 graphite. It's what was fielded in the composite spam. That is the one material we're going to use. So every time we go to do a repair or substantiate a repair, it's based off those materials, along with 93, 96 resin. We chose those materials because those were the materials used on the Comanche, and we had data for days that the Army owned. So we didn't have to worry about resubstantiating that data. In the case of the Gray Eagle, we did validation last month, and we'll be doing verification the last week of this month and the first week of the following month. We expect to have that manual published within during this fiscal year. It all depends on how long it will take to get through ALC. The other thing we've been asked to do is training. With the advent of advanced composites, the current training regimen the current way that we were training to repair composites wasn't going to fit the way advanced composites were going to have to be maintained. Fort Eustis stood up training advanced composites in July of 2013. They graduated the first class that had gotten the training. And I believe the fiscal year starting next year, they'll add 2 weeks of training just for advanced composites. And that's great. However, that was training privates coming out of AIT. None of their leadership understood how to actually execute these repairs. So we were asked to stand up a training regiment to train a couple of specific repairs to the Mike model stabilator, and we have done that. We've also branched that out, and we've trained AMCOM LARS and some engineers from RD Econ. This year, we were asked to stand up a technical inspector course, not to train a new technical inspector, but to take current technical inspectors and train them how to inspect advanced composites. Again, it was one of those things that Fort Eustis just hasn't integrated that quite yet, so we were asked to go ahead and jump on that. So that's another course we offer. The other thing is if you look there at the lower left hand, is CERTEC. CERTEC is an industry certifying body. They have stood up a composite certification course for contractors and technicians so that they can go and get a certification in performing advanced composite repair. The difference about this certification over some of the other ones that are out there is this is a certification where it's performance-based. You take a written test, but then you have to go to an examiner, take a performance-based test actually doing composite repairs before you can get your certification. It also requires that you have some training prior to taking the certification, so you can't just study for the test and then take it. You have to have some sort of substantiated real training to do it. We also partner with Abers Training out of Reno, Nevada. They're a great industry partner of ours. They will custom tailor their training based on the needs that we give them. So if we need to export training to another entity, Abers is more than happy to do that for us. And I believe that's my last slide. Do I have any questions?
Sir, Mark McCoy, I'm the process improvement engineer for the depot, and I got a question about that blade clamp. Has there been any consideration for any engineering design that would preclude the ability to install that or to attach it to the blade incorrectly? Are we too far down the road to re-engineer that?
I made that recommendation. I'm waiting to hear back.
Hey, my name is Trent Mulcrone, McNally Industries. A little bit of a surprise to see our name up there. It was just recently that we learned of that issue with the blades. The blade clamp has actually been fielded for over a decade, and it's my understanding that this is a relatively new occurrence. I went to Fort Rucker and I investigated a couple of the blades that they had there, and it was found that one of the clamps they had they replaced a threaded rod in the back clamp assembly that has a shoulder when we send it to the soldier. They replace it with a full threaded rod. There's no stop. You can tighten it down as much as you want. And that would make sense that it would cause a void. Now, we recommended to the PM that they can remove that rubber pad. Absolutely, 100%. It will not affect the tool, and it should solve the problem. They have not done that.
Right. Like I said, there's nothing wrong with that clamp. It's a great clamp. It's the training of the people using the clamp. If it's used properly, works great. In fact, I think it's better than the legacy clamp.
Thank you. Absolutely. And push to get that rubber pad removed because you can absolutely do that, no problem.
Anything else? Oh, Roy.
So what are we doing to try to advance the requirements as we go to continuing to put advanced carbon fibers in our fuselages of what are requirements for those fuselage repairs and how to accomplish those environmental type repairs on wing instead of being able to go into a shop environment like the stabulator and those things. What are we doing to try to work that?
It's gonna, the most common answer you will hear from anybody who works in the composite industry, if you ask them a question, the most common answer you're going to get is, it depends. If it's a loaded airframe, then just like any metallic structure, you would have to unload it. Other than that, almost anything that can be done on aircraft with metal can be done on aircraft with advanced composites. It is better to keep it outside of the elements because water and moisture are a bad thing when it comes to composites. But it can be done on airframe. With, I think the next big composite structure coming is in the next few years is going to be the composite tail boom for the Apache. We've done a little bit of work with them to look at how it's going to be repaired, and it should be very supportable. The current training model that Fort Eustis has should support it. We don't see it being any huge issue.
Okay. Thanks, Earl. Our last presenter will be Kevin Rees.
Thank you. So this is my worst nightmare. I have to talk after a bunch of smart guys and before the colonel, and we're already late. So, so I'm gonna keep this brief. I want to talk to you just for a couple minutes about how we look at and consider new technology for repair development. I work with a bunch of really smart engineers, and you've heard several of the guys already on this panel talk about this sexy technology or that sexy technology, and that's how we think. So I'm going to tell you about how we try and temper our appetite for all these different neat technologies. So first of all, we consider implementing new technologies based on two things. We look at the maturity of the technology and our motivation, the Army's motivation. How serious a problem are we solving? So I want to talk to you about technology maturity. And there we go, not just you. So there's a thing called a TRL level, technology readiness level. And there's several different scales. NASA has one, DoD has one. They just about all start at 1 and go to 9. And 1 is the least mature, 9 is the most mature. And all it takes to go from 1 to 9 is time and money and luck. You might think of TRL 1 as alchemy, turning lead into gold. It's a great idea if we could just make it work. That's TRL 1. And then TRL 9 is something that we've been doing for a long time, and everybody does it, like chrome plating. So that's the basic scale. Things being done at TRL 1 through 4 are typically being done in a research lab. 5 and 6 we're doing prototypes, and then 7, 8, and 9 we're actually trying to get it done in a real world on a shop floor or a manufacturing environment. And in the excuse me, in the government, we also have different funding streams for all of that. You have your S&T dollars for the lab, your acquisition dollars for the prototypes, and your AWCF or OMA dollars for the sustainment. And so one of the challenges is bridging those gaps. That's why you'll see sometimes a technology develop so far and then kind of stall out because the people doing the development had S&T money, and now you got to wait for somebody with APA dollars to pick up the baton. So that's just as a side note, in case you wonder sometimes, whatever happened to that? Well, the S&T guys are done. That's what happened. Okay, so if you think about this technology maturity, as I mentioned earlier, then relate it to, what is our appetite for that? How far back do we want to reach? Since we know it's going to take time and money to get it, mature enough to where we can implement it, why would we reach back and how far would we reach back? And I gave you just sort of some ideas. These are not absolute hard and fast rules, but in general, if a new technology is nothing but an alternative to something that already works fine, we're not going to reach back very far. We'll wait for it to be a mature technology, and then we'll look at it and say, okay, maybe it's a little bit cheaper, a little bit easier, then we'll do it. If it's an improvement over what we're doing, then we might be willing to reach back a little bit farther and go after a TRL 8 and put in a little bit of time and effort to mature it. If it solves a problem that we cannot solve now, then we might be willing to look all the way back at a TRL 6. And I'm speaking as a sustainment engineer that's working in the sustainment field. So obviously there's other engineers in research labs that are reaching a lot farther back, but we really aren't typically looking at anything that's below a TRL 6 because we've got too many real world problems and alligators snapping at us today to be thinking about something that's still in the lab phase. Okay, so that kind of gives you our thought process in comparing maturity and motivation. So why do we pursue these new technologies? So there's basically two reasons that we go after a technology project. First of all, y'all have heard of the good idea fairy? That's our depiction. I had a summer hire engineering student helping me put this presentation together, and I told her about the good idea fairy, and she came up with this. So sometimes, you know, somebody comes along with a technology and says, here's this great technology. I don't know what you could use it for, but it's really cool. So, you know, that's one way that we look at it and say, oh, you're right, it is cool. We might be able to use it for thus and such. A little bit of that's going on right now, not to pick on Scott, but a little bit of that's going on right now with the 3D printing. You know, wow, this is really cool. Can't we 3D print something? You know, and there are times when it works great. So sometimes we just get a technology presented to us, a solution looking for a problem. And then other times we have a serious problem. We have a part that's breaking and we don't know how to fix it, and we go looking for technologies. So sometimes the project starts with the solution, sometimes it starts with the problem. So how do we pursue these technologies? Now I got a flow chart here, and the font's real small, and I'm behind, so I'm not going to spend a lot of time on this. This will be in the proceedings, but basically this is when we have the technology, the solution presented to us first. And it could be anybody in the aviation enterprise that comes up with this technology and says, wow, this is something really cool. I think it'll help us with, and we start looking at that. And we compare it to those basic motivations I was talking to you about. Is it going to be better than an existing process, or a replacement for an existing process, or is it going to solve a problem that has no solution right now? And then based on those things, that tells us how aggressive we're going to be in pursuing that technology, or how much we'll just kind of sit back and wait and see if it matures. And then those links there, go to that next flow chart. There we go, which is when we have a problem. Somebody in the logistics or aviation enterprise says, I've got this part, I can't repair it, I need to repair it, help me come up with a solution. And we'll go looking for technologies to address that specific problem. And again, we're looking at you know, how mature is the technology, how does it relate to my problem, how much better is it than what I have today, how big a problem is it, and that's how aggressive we are at pursuing that new technology. So main reason I put those flow charts there for you, well, there's two reasons. One, I'm an engineer, so I got to have a flow chart. And then the second one is to convince you that we really do have a process, because I know sometimes our customers think that we're just, you know, obstinate and aren't willing to work on it. We really do have a process.
I believe it when I can read the print.
It'll be in the proceedings, sir. Come on here.
Kevin's my favorite engineer.
Can you hit advance for me there? Oh, there we go. Whoop, now I really went for it. All right. So this kind of addresses a question we heard a couple minutes ago about qualification. And there isn't really a simple answer for that, which is probably typical. You hear that a lot from engineers. There's no simple answer. But we have to look at the individual part or technology we're looking at. We need to understand the actual, you know, blueprint limits, the manufacturing limits, the overhaul limits. How do these parts fail? What are the consequences of the failure when they do fail? How are they loaded? And then that helps us decide just how much qualification we have to do. And then also how mature is the technology. If this is the first time we're using this, then we're going to have to do some basic qualification methods, you know, maybe some coupons and things that once we get that, that technical information, we won't have to in the future. And a lot of times what we do is this crawl, walk, run approach. As you heard earlier about the additive manufacturing, we started with a non-CSI, right? That's what we look at. We're using cold spray. We started with a non-CSI, then we go into a little lightly loaded part, then we go for the whole thing, so the heavy structure. So that's kind of typical also. This isn't a new thing for us. You know, today's routine technology was an emerging technology not that long ago. In the 70s and 80s, we were doing inertia welding, and we were qualifying TIG welding and thermal spray, EB welding. You know, there was a day when EB welding was something new and different that we really had to work on, and now we kind of take it for granted. And yeah, there we go. All right, so, and then the same thing in the 90s, you know, now the water jet stripping that we take for granted was something new in the 80s and 90s when we started it, and now what we're looking at is cold spray, thermal printing, other additive technologies. So we're doing the same, following the same path with these new technologies as we did with the old ones. I won't name any, but I imagine a lot of the folks here can think of when we maybe stretched a little too far for a technology, you know, because it just really was exciting and interesting. And we spent a lot of time and money and ended up with something that we had to, you know, send to Dermo when we were done with it. So this process is to try and keep us from avoiding those, repeating those painful mistakes of the past, and imposing a little discipline on ourselves and deciding just how much time and money we want to invest in one of these pursuits. So I believe that's it. Thank you.
Question? Okay, we are running a little bit late. We have maybe one question. Anybody? All right.
Thanks, guys. Thank you very much.
I know a lot of you understood all that. A lot of that, my eyes were rolling. Being an operational guy, I didn't understand about half of it. But I'm glad there's people in the world that understand that stuff. Okay.